This lesson we'll be looking at a couple of graphs that are a little bit different to the type of graphs that we've seen so far in this course. So we'll just work through one example together. I'll give you the function f of x equals x plus 1 plus 1 over x plus 3, where we have x cannot equal minus 3. What we'll do is we'll go through and sketch this graph, and we'll go through the steps necessary to sketch it. So looking at things like the asymptotes, the intercepts, and the stationary points and their nature as well. So all the information that we'll need to go ahead and sketch it. The first thing we'll look at is the asymptotes of this graph. So there's a couple of things we want to consider. The first thing we want to consider is the behavior for very large x values. Now, if we look at this function here, if I was to substitute in a very large x value into this fraction over here, this fraction will become closer and closer and closer to 0 the bigger this x value is. So what that means is that as x becomes very large, we're going to have an asymptote that is simply equal to y equals x plus 1. And we call that type of asymptote an oblique asymptote. It's not vertical or horizontal. Call it an oblique asymptote with equation y equals x plus 1. So just this first component of the function here. Alrighty, the other asymptote, and it's given away in the question, is when the question tells us that x cannot equal minus 3, we're going to have a vertical asymptote. And the way we can go about that, if we weren't given this restriction in the question, would actually just be to look at this second component of the function here, this fraction, and look at what values of x will give us a denominator of 0, because that will make it undefined. So we could solve this denominator here equal to 0. X plus 3 equals 0. So x equals minus 3 is the vertical asymptote. The next thing we'll look at are the axis intercepts. So axis intercepts, like usual, to find the x-intercept, we'll solve the function equal to 0. So we'll get 0 equals x plus 1 plus 1 over x plus 3. If we tidy that up, we'll bring this over to the other side. We'll get x plus 1 equals minus 1 over x plus 3. Multiply the x plus 3 out, we'll get x plus 1 times x plus 3 equals minus 1. Expand that out, x squared plus 4x plus 3 equals minus 1. Bring the minus 1 over, x squared plus 4x plus 4 equals 0. And you'll find that we've got perfect square x plus 2 all squared equals 0. So x equals minus 2. So that's our x-intercept. Alrighty, to find the y-intercepts, we'll solve the function x equals 0. So we'll get f of 0 equals 1 plus 1 over 3. So I've just gone ahead straight away and subbed in x equals 0 into our original function. So f of 0 equals 4 over 3. So therefore, the y-intercept equals 4 over 3. Alrighty, so we got the x and y intercepts there. Now let's go ahead and find the stationary points. So you can see we're slowly determining all of the information we need to sketch this graph. We've got the equation of the asymptotes, we've got the intercepts. Now we can look at the stationary points. So remember, stationary points, we want to solve the derivative equal to 0. So we want f dash x equal to 0. Now, our original function, if we take the derivative, we've got f of x equals x plus 1, and I might rearrange it to make it plus x plus 3 to the power of minus 1. Now, we can go ahead and use the chain rule there, and if you'd like to do that in your own working, you can, but I'll just jump straight to the derivative f dash x equals 1 minus 1 over x plus 3 squared. Now, stationary points, as we've got, we want to solve the derivative equal to 0. So let's solve this here equal to 0. What I'll do is bring this component here, the minus 1 over x plus 3 squared, over to the other side, because we'll have 0 equals 1 minus 1 over x plus 3 squared. So 1 over x plus 3 squared equals 1. Let's tidy that up a bit. We'll get x plus 3 squared equals 1. So if I multiply that with the 1 on the other side of the equal sign, then we'll get x plus 3 square root both sides equals plus minus 1. So x is equal to minus 3 plus minus 1. So we'll get x equals minus 2 and x equals minus 4. So those are the x coordinates of the stationary points, but to determine the actual stationary points, we'll sub those values into our original function. So f of minus 2 will give us minus 2. I'll just go straight ahead and substitute it in. Plus 1 over minus 2 plus 3. That'll give us 0. So we've got a stationary point at minus 2, 0. That's one of them. And then the other one, f minus 4 equals minus 4 plus 1 over minus 4 plus 3, which equals minus 4. So we've got another stationary point at minus 4, minus 4. Alrighty, let's go ahead and determine the nature of those stationary points. So we'll set up our little table, x, f dash x, and the shape. We want to pick a point that's smaller than minus 4. We'll choose minus 4. We'll choose a point that is bigger than minus 4, but smaller than our other point. So let's go minus 3.5. I'm also going to put in the point that we had our asymptote. So we had our asymptote at x equals minus 3. So let's put in minus 3. And then our other stationary point was at minus 2. So let's have minus 2.5. So a point smaller than that, minus 2, and then a point bigger, 0. So we know at minus 4 and at minus 2, the derivative is equal to 0. Those were our stationary points. And we know at minus 3, I'm just going to write an n to represent that. That's the asymptote. So there's not going to be any graph going through that asymptote, that point x equals minus 3. Alrighty, if we sub in minus 5 into our derivative, I'll go through this quite quickly. If we sub in minus 5 into our derivative here, we'll get minus 5 plus 3 is minus 2, minus 2 squared gives us 4. So it'll be 1 minus 1 on 4, so 1 minus a quarter, which is 3/4. So that's positive. So the shape will be increasing. We know the shape at these 2 points is the stationary point. If we sub in minus 3.5, same process, go back to your derivative, sub in x equals minus 3.5. You should find that it is negative, so it's decreasing. So we know this point here is a maximum. This minus 4 stationary point is a maximum. Minus 2.5, if you substitute that in, you should get a negative. So it'll be decreasing. Sub in 0, you should get a positive, so that will be increasing. So we know this stationary point here at minus 2, 0 is a minimum. Alrighty, so we've got all the information we need. Now we can go ahead and graph this. Alrighty, so I've just gone ahead here and shown you a graph of this function with all of the features that we just found. So firstly, we found that oblique asymptote, which had an equation y equals x plus 1. So that's a really key feature of this graph. We found that as we looked at the behavior of the function for large values of x, and we found that an oblique asymptote of y equal x plus 1. We found a vertical asymptote, x equals minus 3, so that's that asymptote, that vertical one there. We found a intercept, a x-intercept of minus 2 up here, and we found a y-intercept of 4/3. So that was out as the y-intercept there, 4/3. That's the x-intercept there of minus 2. So notice we only found one x-intercept, so it just touches, it doesn't go below, it just touches the x-axis there. And then we found our stationary points, minus 4 was a maximum, and the stationary point minus 2, 0 was a minimum. So that x-intercept that we found happened to also be the minimum turning point of the graph. So hopefully that's been a helpful introduction to some of these graphs that we'll be looking at next lesson.